Okay, so this is really my last topic. If there's extra time, I will cover some other things about acids. But really, buffers is kind of the last thing I need to really cover. So, what a buffer is an aqueous solution that contains substances that prevent major changes when small amounts of acid or base are added to it. So, how could something prevent pH change when you add acid or base? Now, realize, we're talking about small amounts. You don't have to add very much acid to change the pH by a lot, right? If the pH of something is like 4, that means the concentration of acid is 10 to the negative 4th, or the concentration of hydronium is 10 to the negative 4th. It doesn't take much, right? In order to prevent this change, you have to have two things in it. You have to have a substance to react with and remove any base that you add, any hydroxide. Well, what could react with base? An acid could. Okay, great. Well, we also need something that could react with and remove the acid. Right? Well, what could remove the acid? A base could. Well, we need to have a system that has an acid and a base in it. An acid to react with any added base, and a base to react with any added acid. But there's a problem here. What happens if I put an acid and a base together in the same container? They react with each other. How can I possibly have an acid and a base together? Well, the only way to do that is to come up with an acid and a base that don't react with each other. Let's think about this. What if I have acetic acid? What happens when acetic acid reacts? It makes two things. It makes acetate and hydronium. What I really care about here is the fact that, notice, and remember, this system is at equilibrium. So if it's at equilibrium, that means I have this and this. What is this? This is an acid. It's acetic acid. What is this? It's acetate. It's a conjugate base. And because acetic acid is a weak acid, this is not a slouch as a base either. It's a reasonably strong base. It's still weak. It's in the weak category. But the point being that I now have an acid and a base, and they don't react with each other because they can't. If they were to react with each other, if this hydrogen were to jump from here to here, I would have just turned this thing into the acetic acid and this thing into the acetate. They can't annihilate each other. They can't neutralize each other. So, a buffer is composed, and this is the key thing. A buffer is made up of a weak acid and its conjugate base. Right? A weak acid and its conjugate base. So, the fact that it's a weak acid ensures there'll be significant amounts of each, and you have an acid to react with any base and a base to react with any acid. In our blood, we have a buffer because our pH, the pH in our blood needs to stay about 7.4. If it deviates from that by very much, very bad things begin to happen. Well, the acid that the buffer system we use, the acid are what am I trying to say? Our body uses a buffer system to keep the pH right about here. And so where this comes from is our body uses what it has available. CO2, we have CO2 in our lungs. It gets absorbed into our blood. Now, CO2, when it dissolves into water, and this is actually something we see at room, like just with water that's sitting open, it dissolves and breaks into and turns into, carbonic acid, right? Now, in turn, this is going to dissociate into, it's going to react with the water, and it's going to make H3O plus and hydrogen carbonate. The buffer system in our blood is carbonic acid and hydrogen carbonate. it doesn't really get around to dissociating out to the carbonate. We just have mostly this. Now, this would be more acidic, but our body is able to adjust it to keep the buffer at the right range. And it's not as acidic as you would really think. The other thing that's really critical about a buffer is that in order for it to be effective, the acid and the base have to be in relatively equal concentrations. They have to have similar concentrations. They can differ by as much as a power of 10. So you could have up to 10 times as much of your weak acid as conjugate base or vice versa. Any more than that and the buffer isn't very effective. So let's go back to acetic acid and acetate. If I have acetic acid and acetate in my system as a buffer, right, then when a strong acid like HCl is added, right, then what happens is you get the HCl is a strong acid, and it immediately dissociates, reacting with the water to make hydronium. But that hydronium is going to react with the acetate that's in there and go back to water. And you'll shift the balance. You'll make some more acetic acid, but you haven't allowed the concentration of hydronium to increase appreciably. The strong base, like hydroxide, sodium hydroxide, the exact opposite happens. The hydroxide reacts with the acetic acid in there, and yes, while you shift the balance of the hydronium, of the acetic acid and the acetate a little bit, you don't allow a buildup of hydroxide. So yes, it resists changes. It doesn't stay exactly the same, but the change is a lot less. So a couple things are important. If the concentration of acid that you added, if the amount of acid you added was way more than the amount of the conjugate base you have in the buffer as part of the buffer system to react with it, then it would just exhaust it all. And this is what we call exhausting the buffer. So the more of the conjugate acid and base you have, the more resistant the buffer is, the more the buffer can take before breaking. So the ability to react with any, it prevents the pH from changing. They can't keep it absolutely constant. So if you add a base, the pH, drops pH. Addition of an acid, wow, that's weird, still drops the pH much less than it would in pure water, but it still drops it a little bit. Buffers can be overwhelmed. If you add enough acid to completely exhaust one of the two components, the buffer is said to be exhausted. So the more you have, the better. And additionally, different buffer systems are better at different pHs. One thing I will say, and without trying to go too much into the math, and I'm not going to really explain why, but I will give you this sort of general rule. The pH range over which a buffer can work is within plus or minus 1 unit of what's called the pKa. Now, this is kind of a weird concept, but we talked about what Ka was, and I talked about what pH is. So let's try and put those two together. When we took the pH, what did we do? We took the negative log of the hydronium ion concentration. We've talked about Ka, so the equilibrium constant for a given acid. The pKa is just the negative log of it. So when we look at a carbonic acid, its Ka, and I'm just looking this up on a chart in your book, is 4.3 times 10 to the negative 7th. So if I take the negative log of 4.3 times 10 to the negative 7th, then what I get a number that's 6.37, right? Equals pKa. So our blood buffer, the buffer system our body uses, is would only be effective if you wanted to keep the pH between 5.37 and 7.37. And luckily, well, we're kind of at the upper limit of that, where we want to keep our blood. So the balance, you just have to tweak your buffer. If you want to keep it at a lower pH than the pKa, then you need more acid, more of the conjugate acid in the system. If you want to keep it at a higher pH, it requires a more base. Really is it. It's the balance of the two. And that's why you can only, the whole thing I was saying about it only works up to about a 10-to-1 ratio is the same thing with, same reason, they're actually part and parcel of the same reason that you can only go within 1 unit of the pKa. The pKa is actually the pH at which, if you had, that's the pH at which the buffer would have if you had equal amounts of weak acid and its conjugate base. And you can differ by up to a power of 10. So that's where we can go in either direction. But whatever you set the buffer at, it will hold the pH there with relatively constantly. So I'm going to end on this. All of my lectures are going to end on this note here. I will do this practice, and then we are done. So we're going to talk about each of these up top here. So we're going to figure out whether each of these could be a buffer. So first things first. HCl and NaCl. So what criteria does a system have to have in order to be a buffer? Right? It has to be a weak acid and its conjugate base. Well, if the sodium chloride dissociates, we have chloride, and that is definitely the conjugate base of HCl, but there's another problem. HCl is a strong acid, so this is not a buffer. HCN. Well, here's the thing. This is why I told you have to know those 7 strong acids. HCl, HBr, HI. So here's your strong acids. HCl, HBr, HI, HNO3, H2SO4, HClO4, HClO3. These are all strong. Every other acid you see, consider it to be weak. Okay. How about this one? HCN and KCN. Well, you have to realize that this is going to dissociate, and this will be Cn minus. Well, this is an acid-base, a conjugate acid-base pair, and HCN is weak. So yes, this would be a buffer for sure. HCl and KCN. Well, right off the bat, they're not conjugates of each other. And HCl is a strong acid. That just isn't going to work. NaCN and KCN. Well, these are going to dissociate. But here's the problem. All I have is Cn minus. All I have is I don't have an acid at all. That's not going to work either. Okay. So let's do this next one. The response, right reactions for each of the following. The response of an H2PO4 minus and HPO4 2 minus buffer to the addition of hydronium ions. Okay. So the hydronium ions are going to react with which component? The acid or the base component of the buffer? The hydronium itself is an acid. It will react with the base. Which of these two is the base? This one. This is the conjugate base. So the reaction is going to be HPO4, so hydrogen phosphate, reacting with hydronium to produce PO4. Oops, I'm doing that wrong. It's going to, this is the base. It will take a proton, and I'm messing this all up. It will become H2PO4. I'm going to go ahead and erase these just so I have room to work. PO4 minus, aqueous, and water. Right? Neutralizes the acid by taking that proton away from it. Right? And that's it. The second one is the response of an HCCN minus buffer to the addition of hydroxide. So I've got hydroxide. The hydroxide is going to react with which? The acid or the base? The hydroxide, being a base, will react with the acid. The acid is HCN. And that will react to make Cn minus its conjugate base and water. Excellent. And that's it. That's all I have to say. I may go over a few other of the sections in Chapter 10 if we have time, but this is really the critical stuff. There's a few things with pKa's and Henderson-Hasselbalch equation, but it's not that critical. This is the broad stuff. So I'm going to leave it at that for today.